Hello, everybody. Now I'm going to go over question 4. You don't have to watch these in order. I am going to post them kind of all a couple at a time so you can kind of choose how you want to do them. But this is question 4. So, question 4 in 2015 was a slope field question. It was different than your traditional slope field because normally with questions like this, it asks about separating and integrating and doing things like that from chapter 6. And this one started from chapter 6, the very first part with the slope field, and then it really switched and started doing things from earlier in the year. So, I like that it's a good combination. And it is something that, again, the calculator wasn't necessary. So, part A in this question wanted you to draw a slope field. I wrote some extra notes by mine of just kind of what the slope was and what I was trying to show. I highly doubt they're going to make you draw a slope field on the actual AP test. I think they may make you use one just because this can be very hard to show in a situation where you're taking a picture and uploading. But the way it was scored was 2 points, and they always do 2 points for this. They gave 1 point. There was only one place that had a zero slope. It was this point 1, 2 right here. And then all of your other slopes were here. They actually kind of split it up differently here. They looked at these slopes as 1 point and these slopes as 1 point. So if you had the 3 slopes correct when x was 0, you got a point. If you had the 3 slopes when x was 1, you got a second point. Part B, now we kind of switch gears and we're not talking really about chapter 6 stuff anymore. Part B wants you to talk about the second derivative in terms of x and y and then what that means for concavity. So this comes, the second derivative, it's an implicit question. So this would be the end of chapter 2. But then the concavity piece is chapter 3. So it kind of combines those chapters. So your derivative of your derivative, your second derivative, would be 2 minus dy dx. Essentially, when you do this, if you go back to the original equation, the derivative of 2x is just 2, and the derivative of minus y would be minus dy dx because you have to write it implicitly. Now you know what dy dx is, so before you start really doing any work with it, you want to replace that dy dx with that first derivative equation. You could leave it like that. I decided to distribute the minus sign, and I wrote it like this without parentheses. So then the second part of the question wanted to know in quadrant 2, what do we know about concavity? So I came over here and I kind of wrote down, what do I know about quadrant 2? Well, I know in quadrant 2 you have negative x's and you have positive y's. So if you go back here, if you have a negative x put in here, then you're going to end up having two negatives that multiply together to get a positive. And then if you have a positive y on the end, again, you're going to have even more positive. So no matter what you plug in the second quadrant, you're always going to get a positive second derivative. So you could write that in words. You could say it's positive, or you could write it in symbols like I did. And what that means is positive second derivative means concave up. So negative would be concave down. This one was positive, so concave up. So the way they scored it, they gave 1 point for taking the second derivative. So that's what I did first, doing that implicitly. I think whether or not you distribute the minus sign or not, you're going to get full credit for that point. And then your second point is your reasoning. And truly the reasoning being it's positive, so it's concave up is enough. Part C wanted to know what happens at the point 2, 3. Is it a minimum, a maximum, or nothing at all? So the first thing I wanted to see is what is the derivative value at 2, 3 to see if it even has the potential of being an extrema. If the derivative is 0, if the derivative is undefined, it could be a minimum, maximum. Well, what ended up happening was when you put 2 in for x and 3 in for y into the derivative, you get 1. So it can't be an extrema because it doesn't have a 0 derivative. So that's what I wrote. I wrote since the derivative is 1 and not 0, then it can't have a minimum or a maximum. And they, I think, did something very similar. Yeah, they did the same thing. They put in the values, saw that it was 1, not 0, and said that it can't have either. You get 1 point for seeing what do you get when you plug the point into dy dx, and then 1 point if you understand your conclusion is you didn't get 0, so it can't be an extrema. And then finally, Part D was the challenging part of this question. I know I've done this question before, and I think when I did it before, I did it in a much harder fashion. This way made a little more sense to me, so hopefully it makes some sense to you. I'll try to slowly go through this so I don't lose you along the way. It wanted to know what m and b had to be if y equals mx plus b was a solution. So here's the first thing I wrote down, and I'll try to help you follow my thought process. I wrote y equals mx plus b. And then I took the derivative of that because I know I'm dealing with a different derivative. So the derivative of y equals mx plus b would just be m because m is your coefficient. So think of like an equation that was like 2x plus 5. The derivative would just be 2. It would be that slope, that first value. The derivative of a constant is gone. So I wrote that down. And then I thought, well, I could replace that m value into the dy dx that was originally given to me. So I took this m that I got for dy dx and I put it into the original differential equation and I got this line. m equals 2x minus y. And I decided to solve that for y because I figured if the original problem is solved for y, maybe I should get everything solved for y. Again, this was me kind of just messing around. So I added y to the other side, I subtracted m to the other side, and this was what I got. Y equals 2x minus m. So I have that, and then I have what they want me to show as a solution, which is y equals mx plus b. So I kind of treated it almost like a system of equations. Both of them are y equals. But I did it a little differently. I kind of went through more of a logical sense. And what I looked at with this one, the slope of this line is 2. The slope of this line is m. Well, if they're both true solutions, then that means 2 has to equal m. So I wrote that down. So when I wrote m equals 2, it's just because the slope of this one is m, the slope of this one is 2. I know they're both true equations, so that means m must equal 2. And then I did the same thing with the constant, with the y-intercept. I know that these have to be equal to each other. This negative m and this b have to equal each other. Well, I already figured out that m is 2. So if b is equal to the opposite of m, then b has to be negative 2. And to be honest, when I did this one, I did all of that and thought, I have no idea if what I did was legal. Luckily, it was. I think their work is a little different. When I looked at theirs, I thought mine made a little more sense. Here's how they scored it, though, so I think I got full credit. If you knew that you took the derivative of mx plus b and just got m, you get a point. If you then took that m and plugged it into your derivative equation where dy dx was, you get another point. And then if you came up with your answer, they don't say how, so I think I did the right algebra, and the answer is m is 2 and b is negative 2, you get the third point. I feel like I kind of like backed my way out into that answer, so I understand if you look at that and go, what in the world did she just do? And you replay this video again. But in the end, it kind of made sense to me. And I know I've done it a different way before, and I actually like this way better. So again, I wrote y equals mx plus b and took the derivative, replaced that derivative where the dy dx is into the original differential equation, solve for y, so I have two equations solved for y, and then kind of set the slopes equal to each other and the y-intercepts equal to each other and finished it. I think this was the hardest part of the question, and it was worth 3 points. And I actually thought the first point was pretty easy. After that, it got a little messy. So that was question 4. So hopefully that was a good review of a little bit of chapter 6, a little bit of chapter 2, a little bit of chapter 3. And I'm not even sure what I would call this deep part, what part it comes from. Maybe a little bit of like your basic derivatives. So that is question 4. I'm going to continue. I'll make a video on question 5 next so that you can continue going through these questions.